Welcome back. Settle in, get as comfortable as you can. Glad you're here for our continued discussion about the nervous system. So now we're going to get into the details of when I say action potential. We're talking about electricity. We're talking about these concepts that I've just sort of been talking about in general terms. Now we're going to dig into what's actually happening. So an action potential is when a neuron actually depolarizes. So what that means is that you get a rapid change in our membrane potential. And remember, our membrane potential, our resting membrane potential, is about negative 70 millivolts. And that means that the inside of that neuron is 70 millivolts more negative than the outside. Inside of the cell is more negative than the outside of the cell. And so we go from negative 70, so inside of the cell is 70 millivolts more negative than the outside, to positive 30, where the inside of the cell is 30 millivolts more positive than the outside of the cell. And then we go back again. That's what an action potential is. So how do we get there is the question. So we already established that we've got more sodium on the outside of the cell than we do potassium inside of the cell. So just to pull back from our memory, stop and remind yourself, how did we get here? How did we get to a point where we have more sodium on the outside of the cell than we do potassium inside of the cell, and what does that create? What happens? What's going on? Reminding you that ECF is extracellular fluid, ICF is intracellular fluid, so E extra outside, I intra inside of the cell. So hopefully you thought, oh, well, the sodium-potassium pump. Remember, we spent some time talking about the sodium-potassium pump, and what that does is that establishes a resting membrane potential. That establishes the negative inside relative to the positive outside. In addition to the sodium-potassium pump, which remember is a protein embedded in that plasma membrane, in addition to the sodium-potassium pump, embedded in the membrane of a neuron are these gated channels. Gated channels that are also proteins. So these are channel proteins, and they're embedded in the membrane. There's sodium channels and there are potassium channels, and these are critical to the action potential. And also reminding you, extracellular fluid is positive relative to the intracellular fluid at negative 70 millivolts. So introducing a new visual for these things that we've been talking about, this plot, you're going to see this a lot. You're going to see this a lot when we talk about the nervous system, and then you're going to see this a lot also when we talk about muscle contraction. A plot similar to this. The red line is showing you where we start. This is our resting membrane potential, where we're hanging out, where the sodium-potassium pump is busting its butt to keep the neuron at this negative 70 millivolts resting membrane potential. Hanging out here. We're starting at negative 70. Couple of important points about what's going on depending on where we are on the neuron. If we are on the axon of the neuron, if we're talking about what's embedded in the membrane of the axon of the neuron, these channels, these sodium and potassium channels, these are voltage gated. And we'll talk more about what that means in a moment, and I'll show you. However, if we go to the cell body, these are stimulus gated channels, and so that includes the dendrites. So these proteins embedded in the cell membrane of the cell body and the dendrites are stimulus gated, not voltage gated, and that's important. Once again, the membrane of the axon has voltage-gated channels, so it's different. What unlocks these channels, what unlocks these doors is different depending on if you're on the cell body or if you're on the axon. So let's start. How do we get a neuron to fire? How do we get this electrical signal to get passed down the neuron? Well, we have to start at the cell body, because remember, the dendrites are what receive signals. So we have to receive a signal. And that signal comes in the form of some sort of stimulus. We have a stimulus, and what that stimulus does is it causes the stimulus-gated channels on the cell body to open. So in this little picture, I've just put these little red sort of tube things to represent those stimulus-gated channels. So to start this whole shebang, we've got to start at the cell body. Stimulus, something, causes those channels to open. So our stimulus-gated sodium channels open in response to a stimulus. The primary stimulus that we've talked about is neurotransmitters, and that is a key stimulus, probably the key stimulus. But we'll talk about some others later as we dig deeper. So stimulus causes those stimulus-gated sodium channels to open. So they open, and when we open that channel, remember, what do we have on either side of the membrane right now? What is that? That's a difference in charge and a difference in ions, and I can't remember what it's called right now. I'm having a massive brain fart. That is a gradient, concentration gradient. It happens, right? Okay, we have a concentration gradient. We have a lot more sodium outside of the cell than we do inside of the cell. And so now we're pulling in those concepts that we learned when we talked about osmosis and when we talked about diffusion and when we talked about Brownian movement of particles. And so sodium is going to move down its concentration gradient. It's going to move down its concentration gradient. And where does it move? When it moves down its concentration gradient, it moves into the cell. So we've opened the doors. We've opened the doors of the stimulus, and just through natural processes, not using any energy, not using any ATP, sodium is going to flow into the cell, okay, because its door got opened. The sodium-specific door that lets sodium through got open, and it got open because of a stimulus. This is all occurring at the cell body. Okay. If the stimulus is strong enough, the sodium that's moving into the cell changes the membrane potential in the cell body. Okay, so remember that membrane potential is the difference. How different is the charge outside of the cell versus inside of the cell? If we get enough positive charges moving into that negative environment, we're going to change the membrane potential inside the cell body. Okay, so what we're doing is we're just adding positives, right? Okay. What this triggers is something called a graded potential, or what this is something called a graded potential. So this whole lecture, this whole talk is about an action potential, but that all has to start with a graded potential. And the graded potential is what happens at the cell body. So we get positive ions, positive sodiums, flooding into an environment that is negative. So the stimulus is occurring at some point on the cell body, on the dendrites of the cell body. And that stimulus causes gates to open. If the stimulus is strong enough, if we get enough gates opening, if we get enough sodium flooding in, we change the membrane potential. The reason that this is called a graded potential is because it loses strength as it moves away from the stimulus. So at the stimulus, it is the strongest. The further we move from the stimulus, the weaker the change in membrane potential is. So the less of a change in membrane potential we have. Okay? And this whole idea of a graded potential, a graded scale, is familiar to you if you stop and think about it for a second. You're graded on a graded scale, right? So if you turn in work and it's super, super close to accurate and correct, your grade is an A. And the further you move away from the information that is correct, the lower your grade. So this is a graded scale. Graded potential. The further we move from the stimulus, the less intense that change in membrane potential is. The lower the change in membrane potential is. So this is a graded potential. So if we go back to our cell body, remember that we move closer to the axon. There's this super important special place called the axon hillock. And if we get a change in membrane potential at the axon hillock that changes the membrane potential to negative 55 millivolts, right here at the axon hillock, it's bouncing for you right now in green. If we change from negative 70 to negative 55, that's what's called the threshold. We've reached the threshold, and that triggers an action potential. Okay. So we have a graded potential in the cell body. That graded potential loses intensity as it moves away from the stimulus. If it's strong enough when it reaches the axon hillock to have changed the membrane potential from negative 70 to negative 55, then that's going to trigger an action potential. So we're going to step through two scenarios. Do we trigger an action potential or do we not trigger an action potential? So this is our imaginary neuron. At the top is our stimulus. And then what we're looking at is that graded potential moving toward the axon hillock, which is, on this it's labeled the trigger zone. Okay? The axon hillock is that area between the two dotted lines. So in our imaginary scenario, we're going to look at this plot again. And where the stimulus encounters the cell body, where those sodium gates initially open, we get a change in membrane potential from negative 70 all the way up almost to 40, or maybe to 40, so to positive 40. We get a big change in membrane potential. So we're getting a lot of positive flooding into the cell. So at the point of the stimulus, yes, we have passed a threshold, but remember, this is a graded potential. It's going to lose its intensity. Now we're looking at kind of the center of the cell body, and at the center of the cell body, we're only right at negative 55. So the change in membrane potential is just at negative 55 millivolts because it's graded. By the time we get to the axon hillock, we're below negative 55. We're at maybe like negative 60. So the question is, will this trigger an action potential? The answer is no, because we did not reach negative 55 at the axon hillock. Okay, another scenario. Once again, we reach 40. We're at the middle of the cell. We're still at 40. We reach the axon hillock. We're a little bit below 40, but well above our negative 55 threshold. So if the membrane potential is above the negative 55 threshold, do we trigger an action potential? Yes, we do. So this graded potential did trigger an action potential. And it's all about what is happening to the membrane potential. What is the membrane potential at the axon hillock specifically? Okay. All right. So going back to our kind of earlier image, we're on the cell body. We're going to imagine that we've triggered a graded potential. That graded potential is strong enough and it's reached threshold. So our little flashing arrow there is indicating where threshold is. We've reached threshold because we have sodium flooding into the cell. Now we're going to move down. We've reached threshold. Remember, if we're going to reach threshold, that has to be at the axon hillock. So at the axon hillock, that would be indicated by this area. The area indicated by the arrow. What you see is a difference in charges. So above the membrane in the extracellular fluid, now it's more negative. Inside the cell, it's more positive. And this is at the axon hillock. Okay? So we've become enough more positive at the axon hillock to reach negative 55 millivolts. Remember, we started at negative 70. What this does is in the part of the axon that's directly adjacent, right next to the axon hillock, this changes the charge of the membrane. It changes the voltage. And what that does is it triggers the voltage-gated sodium channels in the axon to open. So we changed the charge. We changed the charge enough that it triggered those voltage-gated proteins, those voltage-gated channels to open. So these aren't stimulus-gated anymore. These are voltage-gated. If we open a channel, remember, we're in the axon now. We still have a ton of sodium outside of the cell. So what's that sodium going to do? It's going to flow down its concentration gradient into the cell. Okay, we get sodium flooding down its concentration gradient into the cell. Cool. What's that going to do? Well, it's going to flip our membrane potential, right? It flips our membrane potential, and in the axon, when these channels open, it flips our membrane potential big time. Okay, it flips it from negative 70 all the way up to positive 30. So that's what this plot is indicating down at the bottom. But it does that only at this one specific place, right here, this one little spot on the axon. Okay, right there, that section of membrane, whoop, we flipped things. Where it was negative, we made it positive. Where it was positive, we made it negative. And what that does is it triggers the next set of voltage-gated sodium channels to open. They open, and what does that do? Boom! It flips the membrane. It flips the membrane potential. Apparently very slowly. Come on. It's not moving. Okay, I'm not sure why it's stuck, but it should have the negatives in the extracellular fluid and the positives in the intracellular fluid. And so what we're doing is, if we reach threshold, we're popping along the axon. Those voltage-gated sodium channels are opening in response to the membrane potential changing right next to them. Membrane potential changes, voltage-gated channels pop open. Voltage-gated channels pop open, sodium floods into the cell, changes the membrane potential, causes the next one to pop open. Okay. There we go. Now it moved. Right? So, because these are voltage-gated, we don't have a loss of the intensity of this potential. Okay? Because every time we flip a charge, we open another gate. We flip a charge, we open another gate. We flip a charge, we open another gate. And so the intensity doesn't wane. It stays the same, and it travels all the way down the entire length of the axon. It is not graded. It is all or nothing. If it gets triggered, it travels the entire length of the axon, period. Okay, this is not a graded potential. This does not lose intensity. Okay. So what this looks like on our plot is we've got our negative 70. We're coming all the way up. Okay, that works a little bit better. So at this specific location on the left side of your screen, we go up to positive 30. And then at the next location, we go up to positive 30. And then at the next location, we go up to positive 30. The entire membrane does not depolarize at the same time. It depolarizes in a wave. Meanwhile, we've got our sodium channels popping open. And right behind them, a little bit slower, are our voltage-gated potassium channels. So sodium channels, in response to the change in voltage, they open fast, pop open. Okay, they pop open, sodium floods in, they close. Okay. Behind them, the response of the potassium channels is slower. So we've already got a flood of sodium coming in. We've already got that wave of depolarization moving down the axon, and a little bit slower coming along behind the wave of depolarization, we have potassium channels opening. And if you remember from our discussion of the sodium-potassium pump, where do we have more potassium? Okay. The potassium now wants to move out of the cell. Because we have more potassium, the pump was pumping potassium into the cell, in, right? So we have less potassium out of the cell. So for potassium to move down its concentration gradient, it moves out of the cell. Okay. So potassium now is going to move out of the cell. So now what we're doing is we're pumping positive ions out of the cell. And what that does is it once again flips our membrane potential. So now our plot, we went up positive and now we come back down negative. So potassium now reestablishes that negative resting membrane potential. So we go positive really fast and then we go negative really fast, and we do that at one place on the membrane at a time. Then after this wave of depolarization and our wave of repolarization happens, then our sodium-potassium pump goes back to work, establishing the resting membrane potential, and the more sodium outside of the cell, more potassium inside of the cell, so that the neuron can do this all over again. So a lot of times you'll see or you'll hear an action potential described as a wave of falling dominoes. The reason that it's described this way is because of what I was just talking about how you have this wave of depolarization that happens in one place at a time, then the next place, 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 and how it's triggering the depolarization at the first location. So the falling of the first domino, that first domino has to fall. It hits the second domino. Second domino falling hits the third domino, and all the way down the line. Okay, threshold at the axon hillock, reaching threshold at the axon hillock is this first domino falling. Once that first domino falls, they're all gonna fall. Okay, that is how an action potential works. And next, we're going to talk a bit more about the graded potential. And then we're going to go to the end of the neuron and learn about, okay, so we did graded potential, we did an action potential. What's happening? Why did we make all that happen? What's happening at the end of the neuron?